All right. So, whilst you're digesting, we will carry on. Okay, so let me just briefly recap a few of the main points that I made or tried to make before the break. Sorry about some of the problems with the notebook. Of course, you're quite free to use the Python that Alex translated. Most of you are more comfortable with Python anyway. That's fine. Perhaps what wasn't clear just about the exercise is that there are no instructions in these exercises. I don't tell you what to do, okay? My idea of exercises is I give you code, I tell you the principle, and you go explore, okay? And so for this particular notebook with just the distance inference, what I think you should just try out is, okay, well, you know, how does the posterior depend on the prior and the likelihood? What happens if I change the the fractional parallax uncertainty? What happens if I change the parameters in the prior? What effect does it have on the posterior? You know, how do the different estimates of the posterior, the median, and the mode vary if I change, the fractional parallax uncertainty, this kind of thing. So there are no specific instructions about what to do. So I just encourage you to play. Okay, that's really the idea. Okay, so just to recap, we looked at 3 different types of prior here, all of which have the property of being very simple in the sense that, the first 2, the red and the blue, have, actually all 3 of them have one parameter, okay? The red and the blue, so the red uniform prior, the red and the green just have this cutoff distance, okay? Otherwise they're motivated by being uniform in distance or uniform in space density. And this also just has one prior, which is the length scale at which the exponential decay starts to become significant, okay? And the other thing that I perhaps should have said, if it's not obvious already, is that they're all isotropic, right? They all assume that the galaxy or the universe does the same thing in all directions, right? That's obviously not realistic on a galactic scale, but that's the price you pay for simplicity, okay? You can't both be complex and simple at the same time, okay? So it's always a trade-off between, how precise, how closely do you want the prior to match reality compared to how simple does it want to be, okay? Now, you may argue, well, we should match reality as close as possible, right? Because that will give the best inferences. But what is reality, right? If you're building a satellite to measure the structure of the galaxy and you put in a prior which is already giving you the structure of the galaxy, what are you learning? Okay, so there's an issue there, and I'll come to this in a minute. One thing that I didn't mention, it's mentioned in the papers that I reference, is that these, I argued against these priors sort of on theoretical or principled grounds, namely not being representative in the sense that this is unphysical because it assumes uniform distance, this is unphysical and annoying because it has a sharp cutoff. But they're also bad in a statistical sense if you actually test them. And I won't go into this in too much detail, but one of the tests we've done in one of the papers was we took a simulation of the galaxy using the so-called GUMS catalog. This is the Gaia Universe Model Simulator. We need to use a simulation for this because we need to know the ground truth in order to compare different priors. And we basically assessed, so we created a mock galaxy, if you will, and we pretended to observe it with Gaia. So we measured parallaxes, we added parallax noise to them, and we took that as our input measurements. Then we inferred the distances to all these stars using these 3 priors, okay, and I take the maximum, the mode, each time. Then I compare that distance with the truth that we put into the catalog, okay? And then we can compare that. We can actually get a measure of how well they do. And that's shown in this plot here. So what I'm plotting for the same colors here, the 3 posteriors corresponding to the 3 priors, is the RMS on the distance estimates. It's the RMS over a large sample of stars, okay? So root mean squared difference between the predicted and the true, okay? As a function of the fractional parallax error, okay? And what this shows you that for both the uniform and the uniform space density prior is that as the fraction, of course, when the fractional parallax error is 0, well, there's no noise, so of course the inference is perfect because the posterior is a delta function. Okay, kind of trivial case. But what's interesting with these 2 uniform priors is that as soon as the fractional parallax uncertainty goes above about 10, 20%, then this RMS absolutely shoots up. Okay? In other words, they're very bad estimators. And you can decompose the RMS both into a bias and a variance. So in other words, how big is the random error, how big is the systematic error? And it turns out that both of these explode very quickly. And the reason is what I said before, it's because this cutoff, you have to set it to some fairly large distance to capture the entire galaxy. And once the fractional parallax errors get large, this essentially forces all your distance to very large values. You could say, okay, don't take the mode, take the mean or the median. That doesn't really change the problem. It'll halve the distances approximately, but it doesn't solve the problem. Okay? And it's because these priors basically tell you, well, this prior tells you, in the absence of good data, put the star to a large distance, right? And this one says, well, I don't know where I'm going to put it any distance, essentially, okay? And because it's flat, you know, it'll have a small peak somewhere because of the effect of the likelihood, but it's effectively hardly influenced by the data, it's dominated by the prior. And so this distance is really very uninformative about the inferred distance is very informative about the true distance, and it's highly, highly biased, okay? So it's not just for principled reasons that these priors are not good. If you actually do these experiments, you find that they perform very badly, okay? And somebody asked me at lunch, you know, how does this all relate to frequentist or maximum likelihood estimates? Well, in this context, a maximum likelihood estimate is exactly what it says on the can. It maximizes the likelihood, which is mathematically equivalent here to using this prior. Okay? And so the maximum likelihood estimate in this case is just 1 over parallax, and that's a bad estimator. Not just in principle, but in practice because of this explosion as well. The exponentially decreasing space density prior, of course, it gets worse as the data get worse. It has to, right? Because if your data are telling you nothing about the distance to the star, you're entirely being informed by the prior, and the prior is not going to be likely to give you the right answer for most stars, but it degrades much more gracefully. And the reason is because it has a parameter which you can essentially tune to something physical about the galaxy, you know, a length scale in the galaxy of order a kiloparsec. And so in the extreme case of very, very bad data, the mode of the posterior, you know, the posterior becomes the prior, the mode of this is actually at 2 times this. So it essentially puts all stars at 2 kiloparsecs, which is a much better estimate of the typical distance of stars in the galaxy than whatever this cutoff is at a megaparsec or something. Okay? Now, it's still not a good estimate on an individual star basis, but you know, there's no such thing as a free lunch, right? If there's bad data, yeah, you're not going to get a good distance that is any better than what your prior is telling you. Right? Statistics and probability theory Bayes does not generate information. It's just a way of combining basically data with assumptions or priors. Okay? That's a very important point. Don't look to Bayes to improve your data. Okay? So if you want to know more about this, we've done a lot of testing of this in the papers, so I encourage you to look at those. Okay, so as I mentioned before, you know, none of these priors are very, you know, well matched at all to what we know about the galaxy. So let's try to do that. And my colleague Tri Astromadja and I, but mostly him, wrote a paper in which we explore this in great detail. But let me just give you a very quick summary. This is what we call the Milky Way prior. So the idea here is to do something nearer to our current understanding of the Milky Way. So you can look at this paper, and the first paper we actually sort of develop it in, you know, in a general sense for Gaia, and the second paper we actually apply it to the T-gas data and actually derive distances using it for the T-gas stars. So the idea is to use essentially a star count model for the Milky Way, and these models, of course, themselves are based on previous observations. Right? We didn't invent the size of the galaxy in a model. We used previous observations here to basically determine the intrinsic density of stars in a 3D function, in a 3D distribution, as a function of absolute magnitude. So we essentially build up this function, a 3D density function for stars, depending on also has a dependence on the absolute magnitude of the star. Okay, so it's somehow realistic, according to what you understand realistic to be for the galaxy, of course. And then we use models of the stellar color magnitude diagram, dust absorption, and the Gaia selection effects, okay, to effectively convert an absolute magnitude into a probability distribution over the apparent magnitude, and there, from that also over the distance. And so ultimately what you want to get from this is a prior, okay, which is a prior over the distance, of course, but which is a function of galactic longitude and galactic latitude. So in other words, if you look towards the galactic center, okay, if you ignored the effects of extinction, then you would see, of course, a huge peak at around 8.5 kiloparsecs, corresponding to the concentration of stars towards the galactic center. If you take into account dust absorption and the fact that Gaia doesn't go much fainter than 21st, well, it doesn't really go fainter than 21st magnitude, then of course that peak will move nearer and get spread out. Okay, so it's taking into account the selection function. So this involves a lot of assumptions, right? This model alone has something like 20 parameters in it. So it's arguable whether this is actually better than the simple one-parameter model. Of course, it's trying to match much better the galaxy, but with 20 parameters, and we don't know the galaxy perfectly. If we did, we wouldn't bother building Gaia, right? There are assumptions going in here. So whether you think this is better than the simpler priors I showed you before really depends on what you mean by better, right? It's different assumptions. Okay, so I'm not really advocating one or the other. I'm just showing you that you can do something much more sophisticated in terms of taking into account much more prior knowledge, which is, by definition, having to use much more information and assumptions about stellar evolution, dust distribution, and our understanding of how Gaia observes. Okay? And so, of course, all of this is a lot more complicated now. So the prior itself is a probability density function, which is now, each of these is a plot of the prior over distance. So this is distance here on a logarithmic scale. And each of these panels is for a different galactic longitude and different galactic latitudes. Okay? So here we have, for example, the galactic anticenter, right? L 180, B equals 0. And here we have the galactic center, and you see this peak here going towards the galactic center. Okay? It's not actually at the galactic center because of the selection function. That may not be taken into account here. Sorry, here we actually decomposed it into the 4 different components and then the total. Okay, so you can see just your prior, and this is the whole point, of course, of using a Milky Way prior. Your prior depends on where you're looking in the galaxy. Yeah, that's the whole point. So it's no longer isotropic. Right? And now, yeah. I did. Well, in a very simplified way. I just basically said it observes everything between 6th and 20.7 with 100% efficiency. So it's a very simple version of the selection function. You could, of course, to make it more complicated, take into account the scanning law. Okay? You could take into account differential absorption. You can endlessly complicate this.
But the selection function is included.
Yeah. Yeah. Actually, in these priors, if I'm looking at this here, no, actually, it is. We still get a peak. There's still a lot of stars at the galactic center, even though we have dust absorption. Yeah. Now, of course, the exact dust model you take into account will change these plots dramatically towards the galactic center. So you end up with quite sensitive priors, and that may not be what you want. Okay? Because, people disagree about what galactic model to use, what dust model to use. We even don't know perfectly the Gaia passband yet, so we don't actually know what G equals whatever magnitude is, So there's all these things will play into this. So how does this correspond to posteriors? Well, to get a posterior, we take the prior, multiply by the likelihood, and these posteriors are now shown for a measurement. We imagine we measure a star with 1 milliarc-second parallax. What does that distance posterior look like? Of course, now it's all much more complicated because not only is it a function of longitude and latitude, again, these are a function of distance, but as I showed you before, it depends also on the parallax uncertainty. So each of these curves is for a different fractional parallax uncertainty. Okay. So you're not really meant to read any details off these graphs. You can do that in the paper if you want. This is just to show that if you want to go down this path of having a physically more realistic prior which takes into account more prior information, it's by definition more complicated, yeah, and involves more assumptions. And so, as I said before, you kind of have this, it depends where you are on the spectrum. You can be the minimalist, take the minimalist prior approach and just do something very simple like the exponential decreasing space density prior. It's isotropic, which is kind of dumb, but at least it's very, very simple. So it's sort of robust, right? Or you can go down this route and explain to the referee why you chose these 25 parameters for your prior. Okay. Now, you can do more sophisticated things with hierarchical models and marginalization and so forth that will help you a little bit, but it doesn't change fundamentally the idea that you have to make a choice about the kind of prior you're going to use. Okay, hierarchical modeling just pushes off the choice to a higher level of the inference. Okay. Okay. Questions on this? So, okay, so let me just make some key points to summarize this. Then I want to move on and just say something a little bit about doing inference for clusters, and then we'll get back to exercises, okay? So some key sort of points that I've been trying to make this morning on this. I hope this has come across. Inverting parallaxes to get distances is a bad idea, both in principle and in practice. And one of the ideas of the exercises is to show you the pitfalls of doing this by showing you what actually happens if you do more physically correct approaches to the inference. So you have a high bias and variance. You can look into this paper. And moreover, just inverting this ignores very simple constraints like distances have to be positive. Okay. Priors, of course, play an increasingly important role as the quality of the data degrades. This is again the forest, the deer and the lion and the forest. If the data is no good, then something else has to kick in if you want to learn anything, and that's called the prior. The whole point of Bayes really is to give you a smooth transition between these regimes, not to say, ooh, once my data get worse than so-and-so, I'll chuck them all away, throw up my arms and do something else, right? And that's very important for Gaia because brilliant though it is in terms of going deep and accurate, it turns out that most stars actually end up with rather poor parallaxes. And so if you actually said, well, let's chuck away everything which had parallax uncertainties more than 20%, you chuck away about 80% of the catalog, right, which is well over 1 billion stars. That's a bit of a waste of money, okay? And my point is you can do something with those. Yeah? You need a microphone.
On? Yes, it is. I just had a thought about your comment about priors becoming more important as the quality of the data degrades, which is true. I had a thought about why it seems not to happen in this context that you're working on, that the more data you get, the less the prior matters and things become dominated by the likelihood function, because that's what usually happens and that's the usual story. I think it's that, would you agree that it's because in this problem, the more data you have, like the more stars you're trying to measure the distances to, also the more parameters you're trying to estimate. So it's not like you've got like 5 parameters and you're just adding more and more data and it's getting more narrow likelihood. But
so in all of the cases I've showed you so far, I'm treating every star individually. So the statement that this statement is true because here data degrading doesn't mean less data, it means lower signal to noise.
okay, yeah.
So that's an important point. Often you think about better data meaning more data. But what we really mean by better data is better quality data. So it could be more measurements. For example, I could take many parallax measurements of the same star, but it could just be one measurement of the parallax which has a much lower uncertainty. Okay?
Yes, thank you.
So this does apply, it's just not reflected in terms of numbers of observations. Yeah. But you could make it equivalent because you could take many observations, combine them, and if they're independent, then the quality would improve as 1 over root n to within limits of the systematic. So it's, yeah. But no free lunch here, right? So, if your data are bad, your results are prior dependent. And if you don't want to specify a prior, then you have to get better data, right? There's just no way around that. Okay, sorry. As I said, Bayes won't solve the noisy problem, the problem of having noise in the data, but it will treat the problem consistently across the domain of having perfect data to no data. And that's really its power. Yeah. You have this graceful degradation into the regime of prior dominance, if you like. I should point out that often you don't want to compute a distance from a parallax. Okay? There are many problems that involve distances to stars, but you will never explicitly compute a distance. For example, if you want to know about the absolute luminosity of a star, don't compute the distance from a Bayesian analysis and then shove it in that equation with the logarithm, right? Reformulate the problem to infer the absolute luminosity directly. Okay? And this is almost always true. Moreover, if you're doing some kind of assessment of the quality of your model, let's say you have a model for, it could be the model for the distribution of distances of stars in the galaxy, and that has some parameters, and you want to solve for these parameters. What you could do, but should not do, is derive the distances to your stars, put them into your model, calculate some kind of chi-squared, stir the pot and get out an answer. Okay, don't do that. The reason you don't want to do that, apart from stirring the pot being a bad idea, you should always think about your problem. The reason you don't want to do that is because you almost always want to do model comparison in a space where the noise is well defined. Okay, and the parallaxes have a very, very well defined noise, likelihood, if you will. It's just a Gaussian. So it's far, far better to take your model, get it to predict parallaxes from its distances, and then compare it with the measured parallaxes there, because then you have a very simple chi-squared. Okay? So, if possible, don't compute distances, unless you want to know distances. Right? So don't go away from this thinking you must always compute a distance and then go and do your analysis. That's not the case. I'm really just doing this thing about distance inference as an illustration, but you could equally well do luminosities, whatever, ages, anything. Okay. Okay. Are there questions on this so far? Yeah.
How did the choice of the prior affect the uncertainty? Do you have any thoughts like that one for comparing like the uncertainty with the actual error that you have?
Not.
Yeah. So the question is how the choice of the prior affects the measurement of uncertainty.
Do you mean the choice of the prior or the choice of the parameter of the prior?
What?
Well, how not to answer a question? I'll ask a different one. Okay, the simple answer is no. I don't have any plots in this, but I do have them in the paper. Okay, so I think what you're saying is, of course, so let me just put up just have something to talk about. So this is a plot of our posteriors. Okay, they're scaled, they're not normalized, doesn't matter. So we want to, the posterior is the summary of what you've learned about the distance from the data in the prior. And the uncertainty in the posterior you'd have to quantify, for example, using quantiles or full width half max, or some kind of size parameter, okay? So I think what your question is how does that uncertainty vary for the different priors? Now, that of course depends on what the prior is, and depends on what parameter you have for the prior. So if my prior is a delta function, which says all stars are at 1 kiloparsec, right, then I have the most precise estimator ever, because it has an uncertainty of 0, right? It's perfect. Well, it's actually rubbish because it'll be biased, right? Because it'll put everything to 1 kiloparsec, but it'll be very precise. Okay, so you have to be a little bit careful if you want to assess the quality of a posterior, an estimator from a posterior. You need to look at not just the uncertainty, which is the spread, but also how accurate it is. In other words, how does it deviate from the truth, which you can only really assess with simulations. Okay, so yes, if you look in the papers I referenced, we have quite a few plots showing that. Yeah. So yeah, of course, the prior directly, and the width you choose for the prior has a direct influence or can have a direct influence on the resulting uncertainty, but also the accuracy. Okay, so let me move on to a sort of the next topic now, which is staying pretty much with the same thing, but I now want to look at the problem of what happens if we have multiple distances. So as I said to you before, I showed you this plot here. This is just to remind you what I said before, namely that the parallaxes that we measure within a given field of view, Gaia has a, half-degree field of view or something, will be correlated in the sense that those stars, when observed, will all move in the same direction, right, given the parallaxes. So they'll have correlated parallaxes. And so if you plot the field of view of Gaia, I have no credit for this, I don't know where I stole it from, but it doesn't matter. A nice little picture of Gaia field of view with the CCDs and some stars superimposed. The parallax you measure for these stars will actually be correlated, okay? And it'll depend roughly on the inversely proportional to the separation between them. So the closer they are, the more highly correlated they are. The further the separation, the less correlated they'll be. And so if you want to estimate the distance to a set of stars, say we want to estimate the distance to both of these stars, then we cannot actually do it independently, strictly speaking. We actually have to take into account the fact that their parallaxes are correlated, right? I mean, you could estimate them independently, but the uncertainties you get from them wouldn't be independent. And so if, for example, you said, oh, these are two stars in a cluster, let me infer their distances independently and then combine and average the errors 1 over root n, right? That would be wrong, because you've ignored the correlation in the parallax. So you need to have some kind of model for the correlation. So the first thing you have to do is write down the likelihood now for a set of stars. And this is simple because it remains Gaussian. Okay, so this is just a Gaussian in n dimensions, so for measurements of n stars. So now my parallaxes are a vector, and the distances, I'm using this slightly wrong notation of 1 over a vector just to mean shorthand of the 1 over true distances that you're trying to infer. Okay? But this is a Gaussian still, multidimensional Gaussian in the parallaxes. Okay? And so in principle you can do exactly what I said before, combine this with a prior on these quantities, okay, and infer the distances. But now instead of just the simple variance, you actually have a covariance matrix. And as you know, a covariance matrix has on its off-diagonal elements the covariances between these different measurements. Okay, so now to calculate the posterior, you actually have to know what this covariance matrix is. And this has to come also from some knowledge of the satellite, some knowledge of how these measurements are correlated. And that we don't actually have at the moment. And it's actually very, very difficult to do. And so what I've done in the notebook, you can play with this, is I've just invented a very, very simple model. You can see I'm a great fan of negative exponential functions, okay, because they just are nice. They just go down, which is always good. They don't explode. So I'm just assuming that the correlation between any two parallaxes just drops exponentially with some length scale, which is going to be on the order of the field of view of the satellite. Now, this is a gross oversimplification, of course, because you have discrete effects at the edge of the field of view and stuff. So, but just some kind of idea here. And so this function just tells you how to compute essentially the correlation between the two with two variable parameters, the length scale and also the amplitude of the correlation. Okay, and I have no idea what this is for Gaia, so I just made it up. Right? That's what you do. Right? And this thing here is just the angular separation between any two stars on the sky, which for small angles, keeping away from the poles, is just the sort of obvious, sum of squares of the two angular separations. Okay, I said, don't use this for large angles or near the poles. So this is just a very, very simple correlation model. Okay, and there's something in the exercise in the notebook that you can play with. Having introduced that, I'm now going to throw it away because it turns out for the next problem the correlations create difficulties. So I'll assume they're uncorrelated. Okay, and I'll explain why they create difficulties. So I now want to go on to say, okay, let's imagine that these n stars that we observed in this field of view, let's assume that they're actually part of a cluster. And now what I want to infer is the distance to the cluster. Okay? So in principle, to do that, sorry, I could just, to infer the distance to the cluster, this is my likelihood. Let's just imagine we ignore the correlations. This becomes a diagonal matrix. Then I can just basically say, well, if all these stars are drawn from a cluster and we assume the cluster has 0 size, then the true distances to all these stars are the same. So this just becomes one number, right? And I just try to infer this one number from this likelihood and a prior on that one number. Yeah, I think he needs the mic. You still need the mic, I believe.
Thank you. Is the covariance matrix symmetric? Are the correlations the
Always.
same between? from
Covariance
start-
matrix is always symmetric. The correlation between A and B is the same as the correlation between B and A.
What I mean is the effect. Is it true? Is that true? Okay.
It's true. Believe.
Then yes.
No, don't believe, but we can talk about it afterwards. Yeah, it's the covariance matrix is always symmetric. Yeah. You said it was a short question. I think this is not true. Now go on, if it's relevant, then...
Okay. A covariance matrix for n-dimensional Gaussian likelihood is always symmetric. A matrix is not always symmetric.
No, matrix
So,
not.
if you want your covariance matrix to be physically, how do I say, realistic, what I'm asking is, does the error on a parallax for one star depend on the same way on a second star, then the error on the second star depends on the first? That's what I'm asking.
That's the same question. You just rephrased the question, but I mean, that's basically saying, is the covariance matrix symmetric?
No, because this is your model for the covariance, for the likelihood.
So by definition, a covariance between two quantities is a symmetric function. So if I write down the definition of covariance, right? It's, what is it? The expectation of x1 minus x. Help me here, somebody. Was it this thing, right? Yeah, okay. I should write this as an integral, actually. But. Well, whatever. I'm not going to write it down. Yeah, by definition, it's a symmetric function. So I don't know any situation where you would want to have a... Well, I don't know any situation. Because, I mean, it's just that you know, then if for some reason, I mean, you can imagine some situation in which, you know, this thing affects this thing in a different way from this thing affects this thing, but no, we're not talking about covariance anymore, right? Yeah, but it wouldn't be relevant to this. Okay. Maybe we'll talk about this offline, because maybe there's something more to what you're saying I'm not quite picking up. Okay, so if we assume this very simple, made this very simple model for a cluster where we neglect its size, then the true distance that we're looking for is, of course, the same for all the stars. So it becomes one parameter. Yeah? My likelihood is now n-dimensional, but there's still only one parameter I'm looking for. Okay, so it's basically exactly the same problem as I had before. It's just that my likelihood is now a product of many likelihoods. And it's a product because if I neglect the covariances, you know, an n-dimensional Gaussian becomes a product of n one-dimensional Gaussians. Okay? But that situation isn't very realistic because, of course, clusters have a finite size, like the Pleiades, for example. Okay? And so really, if we want to estimate the distance to a cluster from measurements of the parallaxes of its members, we have to simultaneously take into account or simultaneously solve for both the center of the cluster and the fact that it has a finite spatial extent. Okay, so this is what we're going to do. We're going to a two-parameter problem now. Okay, so I'm picking some stars from this cluster. Okay, and if this was actually done as a demonstration for the first Gaia data release, they were picked out using position and proper motion. So we used prior information about where the Pleiades is. We didn't pretend to rediscover the Pleiades. although there was a second paper that iteratively looked for cluster members. But let's not go into that. Let's assume we select cluster members according to some criteria. I think there are 169 of them. So I have 169 parallax measurements, and I want to measure the distance and the size of the cluster. Okay? My likelihood is well defined because all my parallaxes are Gaussian. I'm assuming the parallaxes are uncorrelated, just to keep things simple for now. It's not strictly true, but let's just keep it simple. So my likelihood's well defined. But I have to define my model because I haven't said what this parameter distance is to the cluster center or size of cluster. I haven't specified that. Okay, just quickly some notation. I'm going to use this funny n symbol thingy to mean a normal Gaussian distribution, okay? Because I can't be bothered to write out this long exponential all the time. So this just means a Gaussian in the variable x with the mean written here and the variance written here, okay? That's just a shorthand. I use bold to indicate vectors, okay? So this R thing is the 3D position vector. And I use this very non-rigorous, dodgy, wrong notation to indicate a vector of 1 over distance to each of my stars, okay? And this thing C is my covariance matrix, which here will actually be diagonal, okay? So it'll just be the variances, the square of the standard deviations, the uncertainties for all the parallaxes. Okay, so here's my very simple model for a cluster. This is us. I assume the cluster is a sphere. Or rather, I assume that stars are distributed in it with a Gaussian isotropic distribution. Okay, so you can imagine a three-dimensional Gaussian, essentially, or if you prefer, a one-dimensional Gaussian in the distance of the star from the center of the cluster, and its position, angular position, is random. Okay, so my cluster has therefore two parameters. It's a Gaussian. If I use x to indicate the distance of a star, the true distance of a star from the center of the cluster, then this has a Gaussian distribution of 0 mean, the center of the cluster, and a standard deviation, which by definition is my size parameter for the cluster. Okay? And this distance of us to the center of the cluster is the second parameter, r subscript c. So I have two parameters, r subscript c and s subscript c, which is the distance and the size of the cluster which I want to solve for. And the data I have are 169 parallaxes to stars assumed to have been drawn from this distribution, okay? That's what I want to infer. Okay, so how do we solve this problem? Well, I have my model for the cluster, I have my likelihood. The key thing here now is to put this together into a posterior, okay? So let me just go through this briefly. I'll leave out a couple of mathematical steps just to keep things a little bit shorter. The first thing you do, and this is kind of illustrative of how you can approach any of these problems, the first thing you sort of want to do is write down, I would always start off by writing down the posterior that I want. Right, that's the first thing I do. Well, after I've defined the problem, the parameters, I then say, what's the posterior I want? Yeah? You know, as you know, whenever you try to solve problems, always work backwards, right? Write down what you want first. So I want to have the posterior distribution of these two parameters, and of course it's given the parallax measurements and given their uncertainties, which is just this diagonal covariance matrix. Okay? And then the key to any sort of Bayesian development is then to try to write that posterior down in terms of things you know. And almost always the first step, or often the first step, is to write down Bayes' theorem. And the reason you want to write down Bayes' theorem is because it does this inversion between the parameters and the data. So it expresses the posterior in terms of the likelihood, which is nothing more than a probability distribution in the data given the parameters. Okay, and that's normally something I know about. In fact, as you'll see in a moment, I actually know something very similar to this. Okay? But often you have to sort of suspend a little bit, you sort of have to have a little bit of faith in where you're going, in the sense that the key thing will be, as you'll see in a moment, to work out this likelihood. Right? This is just my prior over distance to the center of the cluster, so I can just adopt one of the priors I've been talking about before. And this is a prior on the size of the cluster. Okay, we'll come back to this in a minute, but this is going to be something positive because clusters can't be negative size. Okay? And this is just the normalization constant. It it's not a function of my parameters of interest. I don't actually care about it explicitly. I can just use it to normalize this. So I can compute this just by integration later, if I want to. Okay? So essentially, I've reduced the problem of finding this posterior into the problem of finding this likelihood. Okay? Now, this is often the second sort of, well, people use the word trick. It's not a trick, but it's a mental step in doing inference. Often what you want to do in order to work out the likelihood is actually express it in terms of things you don't know. Okay, that seems a strange thing to do. But the reason I'm doing this is because I know through experience that if I can write this likelihood actually in terms of the distances, I'll be able to simplify this because my geometric model here, you can see just from simple geometry that this distance, okay, which I don't know, but if I did, is related to this thing, which I had from my cluster model, and this thing, which is the thing I want to know. And of course, these angles I assume I know. It's the position of the stars in the sky. I assume I just know those perfectly. Yeah. Microphone, there's one coming from the back.
Yeah, very shortly. I don't want to be picky about this, but you're using for the cluster profile Gaussian distribution, right?
Sorry, for the which profile?
For the cluster profile,
Yeah.
yeah. So my first question is why, and if the answer is because it's easier, then my second question is that even physically correct?
So, because it's physically easier is indeed the answer to the, because it's easier is indeed the first answer. I'm just doing a demonstration. You could use a king profile. You could use something else. I'm just doing something very simple.
Exactly, for open clusters, that means that you're going to exclude some members just because of this profile.
Sure, then use something else. Feel free. So what I'm illustrating here has nothing to do with this choice. Okay, if you like, imagine this n means a different distribution shape. Nothing I'm going to show you will affect that.
Okay.
Okay? The important thing is I just want to parameterize the cluster. I want to have a model for the cluster which depends on just one parameter. If you want to have two parameters, fine. It'll end up as a three-dimensional problem instead of a two-dimensional problem. Okay? But I'm just starting very simple for the sake of illustration. The fact that it's a Gaussian is actually irrelevant. Okay? You can, as I said, think of this as your favorite one-dimensional distribution to describe a cluster. Okay? And just keep things simple at the moment. Okay? But, it's a good question. This is not physically realistic. Okay? I don't believe in physical realism, at least not when I'm teaching things. Okay? Just makes things much more difficult. Okay, so my point here is I am, the reason I wrote down this equation, I'll go back to in a minute, is because I have a clear geometric relationship connecting this, which is sort of what I've just added to my equation, with this, which is what I want to know, this for which I have a model, and this for which I know. Right? It's just the cosine law, right, which you learn in school, connects these things. That's my reason to introduce this. But you have to make a little bit of a leap of faith, but you'll see why this is useful. Okay, so all I've done here, this is one of the most useful laws of probability that you'll ever need, is marginalization. Essentially what I'm saying is that if I take the joint distribution of the parallaxes and the distances and sum it up, or integrate, over all the distances, I end up with the distribution over just the parallaxes. Right? This is just simple probability law. Okay? So I've introduced this R here in order to be able to write this down. So this is just mathematically true. It has nothing to do with astrometry, Gaia, Bayes, anything. Okay? The reason so having written this down, of course I don't any better know what this is compared to this, but I can now write this down using the product rule. Okay? So if I just use the product rule, the probability of omega and R, maybe I could just write this. Let me just fill in the intermediate step here. The probability of omega and R is just the probability of omega given R times the probability of R. Agreed? Yeah? Now I just say, oops, I left off the dependencies. What are they? C, RC, SC omega given R, C, RC, SC. This is why I left them off, because it's very boring writing all these things down. Oops. Let's keep it in order. Okay, so generally speaking, whenever you write down a probability equation, you can just say, oh, now let me just condition everything on the same quantities. Okay, that's fine. It doesn't change anything at that stage. Okay, so this is just the basic rule of probability. This is actually what you write down to get to Bayes' theorem. And now I just condition everything on C, RC, SC, which is what I had here. Okay, and then I use, so that's the product rule I've used to get from to here. But then I use this other very important thing, which also Brenda mentioned yesterday, is this idea of conditional independence. Namely, that once I condition on certain variables, I become independent of others. Okay? So for example, if I look at this quantity here, right, this looks a lot like my likelihood. Right? Because I said I'm having a Gaussian likelihood. Right? I have a Gaussian likelihood. So given the distance, yeah, and given the sigma, yeah, that completely specifies my likelihood function. Right? That gives me the full distribution over omega by construction. I've decided that. I have a Gaussian likelihood. It has nothing to do with the cluster center or the cluster size. If I know the distance to the star, yeah, it doesn't matter anymore what the cluster and center or the cluster size are. That will not change my knowledge or the distribution over omega. Okay, so that's called conditional independence. Once I condition on knowledge of these two things, I can get rid of the dependence on those. Okay, just like this is conditionally independent of my age, right? Okay, it's because once I've got this introduced, everything else becomes irrelevant. It's fully specified. Likewise, the true distance, the dependence, the probability distribution over the distance, the true distance of a star, of course depends on the cluster. It depends on where the cluster is and how big the cluster is. But it certainly has nothing to do with what some satellite orbiting the Earth happens to measure the precision of the parallax to be. Right? That doesn't change the true distance, yeah, unless you have some very bizarre understanding of reality. So we can conditional independence get rid of the dependence here. Okay? So conditional independence is extremely powerful. These three things, marginalization, product rule, conditional independence, is often what you used to write down your likelihood in terms of simple things. And I've achieved this because this is just my Gaussian likelihood, right? And this thing is essentially, I have to do one more step, which I will skip, but essentially you can show quite easily that this is just equivalent to this. Okay, because once I know, if I know these angles, then I know where the star is. Therefore, the only unknown is this variable, so the probability distribution over the distance is equivalent to a probability distribution over the distance from the center of the cluster. Okay, that could be a nice exercise just to demonstrate that. Okay, but in the interest of time, let's just take that essentially as equivalent to my statement that I have a certain model for the distribution of the cluster. Okay. So now I know my likelihood in terms of something. I can actually compute this, right? So as I said, this is an n-dimensional Gaussian likelihood. It's actually really very simple because I'm assuming no correlations. So my covariance matrix is diagonal. So instead of this being an n-dimensional Gaussian, it just becomes a product of n one-dimensional Gaussians. Okay, that makes life much easier for me, which is why I did it. Okay. And as I said, you can show that this thing is actually just equivalent, to, again, to my Gaussian cluster model. Okay? So this integral is now relatively straightforward to compute. Now you might suddenly think, oh, it's a convolution because it's a product of two Gaussians. Unfortunately, it's not, because this is Gaussian in R, but this is Gaussian in the parallax, not in Gaussian in R. So it's actually not a convolution. So this is not analytically tractable. So you actually have to do this numerically. Okay? But still, it's not too difficult. And you can do this with kind of a Gaussian quadrature rule. You don't actually have to do MCMC or anything like this. So. Okay. So this is perhaps one of the most important slides I'll show, because it actually just goes through the sequence of events that you do often in inference, and it's often about writing the likelihood here in terms of quantities you know and can more easily deal with. Okay. As I said, I make an approximation, so I make my covariance matrix diagonal, and that means you can now write the likelihood instead of an n-dimensional integral, it's a product of n one-dimensional integrals. Okay? And that's great because doing n-dimensional integrals is very difficult, even with MCMC. Right? So this is why I neglected the correlations, because if I keep the correlations in, I have to do an n-dimensional integral. And I don't like doing n-dimensional integrals. Okay, and so the upshot of this is, once you now use the cosine law, and again I'm skipping a little bit of a step here, you can write down each of these likelihoods, each of these one-dimensional likelihoods as this thing. This is just my Gaussian in x, this is a Gaussian in omega, and you end up with this geometric factor which allows for the fact that actually the stars have finite angular spread. But it turns out that actually, because cosine theta is very close to 1, once the angle is less than about 10 degrees or something, you know, all clusters apart from the Hyades are, you know, less than a few degrees on the sky. So essentially for all clusters, you can actually neglect this factor, which makes the integral much easier. Okay? Oh, the cluster center is already taken into account here. And in here. So this becomes, hang on, have I got this written down? Well, this is only, this is the, sorry, this is the, and where's the, maybe I've made a typo here. I'm just trying to think where the cluster center is appearing. I've got it written in my notes. Let me check that. It's obviously still in there. Yeah. So this is a function just of these two parameters. So this is the likelihood that we're using. Okay, the product of many of these. And so this is in the notebook. Okay. Okay. So let me just summarize what I've done there. Okay, and then you're going to go to the exercise and actually do it yourself. But I just want to make this summary of the points because, you know, if you're not interested in parallaxes and Gaia and astrometry, that's fine. But really what I'm showing you here is just a general approach. This is why I'm not too bothered about what model I've used for the cluster. That's not the point I'm trying to make. I'm not trying to, not for a minute trying to say you should model clusters in this way. Right? But these are the important steps. I would say that, you know, the first thing you should do is identify what your data and your parameters are. Right? What do you know and what do you actually want to infer? And it's surprising how often when people will come and talk to me about problems they're trying to solve, they haven't really worked out yet what are the data and the parameters. Okay, it sounds trivial, but think about it very carefully. Identify your generative model. This is the thing that generates the data. That's what it says, right? In other words, it predicts the data given the parameters. And in this case, this was the cluster model. Okay? This was the thing that said the cluster had a Gaussian distribution, essentially, and was at a certain distance. Identify your measurement model. In other words, how do the measurements potentially differ from what they would be if you had no noise? So it's also called the noise model. In this case, this is just the Gaussian. Okay? Identify what your background assumptions or your priors are. Okay? So in this case, it would be a prior on the distance to the cluster and also some prior on cluster size. So some idea of how big clusters should be. Okay? And again, you look at this in the exercise, you can play around with that prior to see what effect it has. And then the manipulation tools I used, of course, were Bayes' theorem, the marginalization, and the product rule to introduce unknown quantities. And this is the perhaps slightly difficult conceptual step, is that often you will introduce quantities you don't know and then marginalize or integrate over them. It sounds a really stupid thing to do, but the reason we do it is because it allows us to write things down in terms of things we know. Okay, so that's often a very key step. And often it involves writing, and in this case it involved writing down a probability distribution for the true distances given the cluster parameters, and then marginalizing over those true distances. And the reason I did that is because it links what I know about the cluster to what I know about the likelihood, namely through the true distances, because it appears in both. Okay? And then I showed you conditional independence, which we then use to remove terms and make us realize that, oh, that's just the likelihood, oh, that's just the prior, or that's just my cluster model. Okay? And I would argue that this is generic to almost all parameter inference problems. Okay? Okay, and if you want to know about more about this, just very quickly, and then we'll go to the exercise, in fact, which I'll show you now. If you can actually try this out if you like. In the first data release, the consortium published this paper in which we identified various clusters and did cluster membership selection for these clusters. And so there are electronic tables, for example, here for IC2391. The table I've put on in the notebook containing the data for identified cluster members and their parallaxes. So the example I have in the notebook is just for Pleiades. If you want to try other clusters, you can do this. Okay, so I won't go through this, but if you want to know where the data came from, you can go to the Gaia archive and select it. This is just to show you what's in the Gaia archive, but you don't need to do this because I've already downloaded the data for you. Okay, so let's let me just quickly show you the notebook then. Oh yeah, that's a note, by the way. If you go to the archive, don't use Safari for that reason. There's a security issue, you can't log out. Haha, I think I'm still logged in. Okay, so use Firefox. Where's my machine? Okay, where's my notebook? Oh, where's my notebook gone? Okay, I can't find my... it's hiding under here. Okay, so in here, there is this Python, well, it's a Jupyter, it's not Python. It's a Jupyter notebook with R code in it, okay? It's called Distance Inference Multiple Sources, and it goes through exactly what I showed you, okay? So again, it's not questions, it's just puts the code in and goes through the example, and as you can see, it'll region the data in the disk here. It produces the plot, which I already showed you. So always inspect your data before you do any inference. I should have said that, right? Don't just heads down, start doing inference. Look at the data, understand the data. So I just do the plots of the fractional parallax uncertainties and get an idea of what the distance should be just by doing simple 1 over parallax. I think for getting an idea, that's okay. The scale of the problem. If you're interested in what happens if you do the naive parallax combination thing, try it here, see the numbers you get, and then compare it to what you get if you take the Bayesian approach, okay? And I should point out there are notes in here, so read them, they're there for a reason, because it'll say in 2 places, don't do this, okay? I left it in on purpose, okay, so you don't do it. But what you can do if you're interested in just doing the distance estimation, taking into account the cluster size, go down to this block here, infer cluster distance and size, which we neglect the correlations. Where's it gone? And essentially, it'll just take you through it, okay? So you can just run each block of text. I set up a prior here on the size of the cluster. So you can see actually here, this is now I actually changed to kiloparsec, sorry, because the Gaia data in milliarc seconds, so the inverse of a milliarc second is a kiloparsec. It's a bit more natural. So this is actually my cluster prior for the size of the cluster. Play around with this. It's actually a beta function. Here I generate some test data in case you just want to test the function, don't want to use Gaia data. You can use this block of data instead. And this is the thing which actually does the work. And the thing to point out is that I have a 2-dimensional posterior over, remember the thing I'm computing here is right, the 2-dimensional posterior. 2 dimensions is fairly easy to deal with, so I calculate my posterior by brute force on a grid. I just go through and go compute it everywhere. Okay, so I don't use the MCE or anything like this. It's not necessary for a 2D problem. You could do it, but it wouldn't be any faster, actually. And the reason is because you have a reasonable idea already of where the cluster is and how big it is. Okay. So this just, you can see it's doing explicit looping, right, over these two parameters. And then it'll do does some plots here of the two-dimensional density function. So this is the two-dimensional density function here, just plotted as a grayscale, and then the one-dimensional marginals, okay, computed from that. The red line is just my prior. Okay, so have a look at that notebook, play around with it, you know. It takes data from the Gaia catalog. You can choose different stars to compute this for. You can change the priors. You could artificially inflate the errors, this kind of thing. Just to get a feel for what's going on. Okay?
Okay, thank you very much.